So let's move on to the expenditure function on line 34 of your first set of slides for demanding choice. So we have set up the expenditure minimization. Our objective is to minimize this expenditure spent on two goods, X1 and X2, so that our well-being reach the level U bar. So it's like it's fixed at that point. You don't want less than that, but let's say we also don't want more happiness than that. Just we have to be happy at that exactly that level. Okay? And then we have solved from the first order condition for the Hicksian or the compensated demand function, which tells us the quantity needed or the quantity we could consume of X1 and X2, which is function of prices, so that we could attain this utility level, right? So now how to calculate or how to derive the minimum or minimized expenditure needed to consume these quantities of goods. Now remember again, when we talk about utility maximization, after deriving the Marshallian demand function, what did we do to calculate the maximized utility level? We plug the solution for the goods quantity back to the objective function, right? And that, in that sense, we have the indirect objective or indirect utility function. Here we do the same. But now our objective function is expenditure, not utility anymore. So let's do it. So we will have the expenditure function, which is also a function of P1, P2, and U bar, just like the Hicksian demand, equals P1 now times X1 h, right? The solution from the minimization plus P2 times X2 also h, right? Okay, let's do it for the stone-jury cases that we just did before. So in that case, the stone-jury expenditure function will be, let me write it down here. Stone-jury. In this case, E, P1, P2, U will be P1 times X1, which is C1 plus P1 over B1 to the power of B1 minus 1. It showed on your slide earlier. So here I just rewrite it. So P2 over 1 minus B1 to the power of 1 minus B1 times U bar. This is the first part for X1. Plus P2 times C2 plus again P1 over B1. Oh, it's a little bit dense here. So to the power of B1, let's write it a bit lower. So P2 over 1 minus B1 to the power of minus B1. Then again times U bar. So this is the expenditure function. Now we don't have to simplify anything here, no need to do that, but it would be good to realize again, like I stressed last slide, is you have a component P1, C1 and P2, C2 in your expenditure function, which are not attached to anything about your utility. Doesn't matter if that's the given level of happiness or the exponent which is from your preference, nothing like that. So that means that these things or these expenditures of B1, C1, P2, C2 must be consumed anyway, doesn't depend on your preference or utility. You need them to survive before you could think about happiness. No? Okay. Now we come to the next thing. Remember I said earlier in the introduction that even though the Hicksian demands function are used to depict only the substitution effect, right? Not the income effect. However, from the solution of our expenditure minimization problem, we could also derive this income effect from that. How do we do that? Now, very straightforward. Okay, back to the definition of the expenditure function, which show you how much money you need at given prices to attain this level of utility, right? So for that reason, you would have, let's say, a banana. You eat banana regularly. Normally, the price of banana is P1, 0. And one day, it increases to P1, 1. Banana gets more expensive because, for example, there's typhoon in the production area. Okay, so before that, when bananas at this original price, to attain a utility level, let's say U bar 0, the utility or the level of well-being that you want, you would need to consume or you would need to spend this amount of money. P1 is 0 now. P2, for example, all other goods counted as that, like a composite of P2, no? And then U0 bar. So normally you need that amount of money. All right, to maintain your well-being. And then now, if you still want to stay on that level of well-being, you don't want like your health to get worse because you consume less banana, let's say, then you have to spend more, right? Because now it's more expensive. So very intuitively, when it's more expensive, if you want to maintain your consumption as before, you have to spend more. So that will be E P11, right? P2, P11 is the new price of banana, and U0 bar again. So you still want to be as happy as before with banana and everything else in your consumption basket. Now, how will you have to be compensated? So the compensated here, the compensated amount is actually exactly, it would be E P1, 1, P2, U0 bar, minus E, P1, 0, P2, right? So assume Roman realized that banana is very important for our health and they want to maintain your level of well-being as before. Then what would they do? They have to give you some extra amount to cover the extra expenditure that you have to spend on the price increase of banana, right? And this is the difference in the two expenditure amount before and after the price change. And it has a name, actually, I would write it there, which is compensation. Compensating. Variation. So it is the extra expenditure or extra income needed to compensate someone in order to keep him or her on the same utility level when there is a price change. So what about the case where you have a price decrease? Now this, obviously, the CV, the compensating variation, is positive, right? They have to pay you, you need more. But if the price decreases and the state still want you to be on that utility level, no more, because maybe, I don't know, consuming more banana will cause some negative effect to the environment, for example, then they take away the excessive money that you have now. So in that case, the CV will be negative. So positive for price increase and negative for price decrease. Okay. Another thing about the expenditure function which is important and also useful to know is how to derive the Hick or the compensated demand function using the expenditure function. Assuming this is what we're given, we have to derive this. How do we do that? So if you remember last time when we tried to find the Marshallian demand function, starting from the indirect utility function, we first started with the indirect objective function, right? So now let's do something similar here. Let's write the indirect Lagrangian again, which is the function of prices and utility, which is P1 times X1H is a function of P1, P2, U bar plus P2 times X2H, function of P1, P2, U bar again, and plus lambda times the constraint. So the constraint in this case, let's write a square bracket instead, is U H X1H X2H. I don't write it here to save space, but you implicitly understand that it's the same like here, right? Minus U bar, right? Okay. Last time we took the derivative of something. Now we will have a similar approach, but even easier. So let's see. Now if we take the derivative of L with respect to, for example, P1, what will we get? We will get, where's P1? Here, right? So the derivative of this part will be X1H P1 P2 U bar. And where else? No, there's no P1 over here and here. There must be some B1 inside here. But let's now, for now, let's say for sure that the Shephard lemma says that you could derive to the Hicksian demand by taking the derivative of the Lagrange, in this case exactly the derivative of E, right? With respect to P1. How can it be so easily? Because it looks very complicated, right? We have P1 here inside the X, and here somewhere inside also. How could we just have like the derivative like this? The first thing to realize is this objective function is now evaluated at its minimum value already. We solved that already, so it's at minimum. And at minimum the constraint holds. So that is, this term is 0. The constraint holds. The second thing, remember envelope theorem. So that helps a lot because now we can fix the x, like the original variables at its optimum point, and ignore the indirect effect of P1 inside or through these variables, but only examine its direct effect when it stands alone here. So that's why at the end we have this derivative. Now, let's say it's here. Envelope theorem. So that's why I said that it's quite important to know about a theorem. Now the intuition behind that. Try to put it in a real life story. By definition, we have the derivative of the expenditure with respect to P. Now, tells what? Tells us when price change 1 unit of currency, of course, then the expenditure change exactly the amount, which is the value of the derivative evaluated at this point. Now, so that's the definition of the derivative. Let's have another thing over here. So assume you eat, I don't know, X banana every month. Banana. Yeah. And then the price of banana is BNN per banana, right? Originally it's BNN 0. Okay. What happened if this increased to BNN 1? How much more money you will need to buy X banana now? Let's write it down. So originally you need the expenditure E0, which is C plus X BNN times BNN 0, right? C here is a constant, assuming that everything else you consume is in this C and the state unchanged. And then now you have the new expenditure that you need to consume exactly this amount of banana is, let's write here, increase by 1 unit. So price increase by €1, let's say. So E1 would be C set the risk variables, everything else stay the same, plus X banana. You still want to have, for example, 10 bananas per month, as before, no less, times this new price, which is the old price plus 1, right? Now, so you calculate the change in necessary money or necessary expenditure equals E1 minus E0. Equals, you have to take this term minus this term on the left. So C and C is gone. And you distribute this. Let's write it down. So C plus X B and N times P B and N 0 plus X B and N, right? Then minus C minus X B and N times P E and N 0. At the end, what you still have is the term is gone. Equal X E and N. Now, so if you eat 10 banana, now each banana is an extra euro. Then you need 10 more euro, and that's the very intuition behind what we just derived here with Shephard's lemma. And you might ask yourself, okay, why do we need like every name here for everything, like every single step that we do? It sounds to some of you will be very obvious. The thing is, you know, in the history of knowledge, it didn't come so obviously. So it took a lot of research, thinking to arrive in what is here. So the person who brought this piece of knowledge up deserved an acknowledgement. So that's why we need the name of these steps over here. So try to remember that. Okay?